Okay, I'm going to try this again. I'm going to try to make this one down to keep it under 10 minutes. So I'm going to talk about refraction. And remember, we talked about that today in class. This is going to be a good little review for you. It's about the bending of light as it enters into a new medium. And the first thing I'm going to say is that when I wrote that formula down off the top of my head about what is the index of refraction and how it was a ratio of the speed of light to that of a speed of light in a medium. So that ended up being n, which is the index of refraction, n, is equal to c over c medium. So I think I might have put it the other way around today. Just check your notes and make sure. Anyway, that's how we find the index of refraction. If you recall, refraction was it was when light entered a new medium, it got bent a little bit and it got redirected. And so we're going to go ahead and focus on that right now. So if you recall, I had like a little pool of water here, which we know has a higher index of refraction than air. So this is air out here in the outside. And remember that we had a ray of light coming down and hitting right there at the interface between the air and the water. And then there's the normal that we just drew. So we know that n air is less than n water. And so because of that, because n air is less than n water, then we know that this ray of light is going to bend towards the normal as it transmits through this water. And if we talk about this angle, this is theta incident. And then we talk about this angle, and this, I'm going to have to come out here and do that. This is theta refracted. So when in the case where the index of refraction outside that the light is in, and then is less than the index of refraction that it's transmitted into, then we know that theta incident will be less than theta refracted in this case. Now here we're going to go down here. We're going to put a new normal where the light in the water is now going to exit out of the water back into the air. And so now we know that the index of refraction of water is greater than that of air. So now the ray of light is going to refract away. Oh, there did it again. Okay, there we go. Away from the normal. And actually, I'm going to rewrite that because it should come right in at the exact same angle. It should refract back out. So this is theta refracted in this case, and then this would become theta incident. So let's just sort of trace the ray of light path through. So here we go. It's coming. I'll just do it in a different color, tracing over it, maybe in red. And so here it's coming through, hits the interface. Now we know that part of it will reflect, and that's that law of reflection we talked about. We know that this angle and this angle will be the same. And then it refracts, bends towards normal. It did that because the medium which it went into is greater in density, or the index of refraction is greater than the index of refraction that it presently is in. And then it's going to exit back out, and it will refract away because the index of refraction that it is in is greater than the index of refraction which it is going into. I hope I said all that right. So I'm going to jump you back a slide here, and just to remind you that that is how you define the index of refraction. It's a ratio of the speed of light in a vacuum to that of the speed of light in the medium. And medium could be air, glass, water, a crystal of some sort such as diamond. And so anyway, that's the index. That's refraction. Pretty simple. So you can see refraction commonly on beaches and that, where a wave front comes in, and as the wave comes and approaches the beach, it always tends to hit it parallel to the beach. And that's simply because as the wave comes into the beach area, it actually hits the bottom of the ocean, thus slowing down that segment of the wave, while the part that has not hit the bottom of the ocean, so you know what I mean. Here's the beachfront, and then if you have waves coming in, like wave crests coming in, And then as this wave starts to approach the beach, this part right here is going to slow down, and this part will go faster, thus causing the wave to turn until eventually it's parallel. I don't know if that makes sense to you, but it's pretty simple. All right, going on. So let's take a look at what happens to white light when it's incident in like a prism. So I showed you a prism today in class. So let's have a ray of light come in and hit right here. There it is, coming in, hitting, and here's your normal. I'll put the normal in a different color. We'll put it in a pretty blue. And so there's your normal right there. And so now this is, I'm going to go back to my red. So this is a glass prism. And this is air. And so we know that it's going to bend towards the normal. So this is a bit tricky, but think about this. So now the ray is going to bend down this way towards the normal. But what's interesting is that how much remember that light is made up of those colors. You all have learned it in school. It's the mnemonic for it. Roy, G, Biv. Red, orange, yellow, green, blue, indigo, violet. Those are the colors that make up white light. All put together, they create white light. Take away any one color and you get a different color of light. And what's interesting is that the red has a different frequency than violet, and actually the frequency of light increases as you go from red to violet. And so because of that, there is a slightly different, it sort of creates a different index of refraction. They act differently, they bend differently because they're all different components of light. And so what you end up seeing is that red bends less than violet. So this will be red, and then, see if I can find a pretty violet here. Here's violet, somewhat violet, and violet will bend more towards the normal. So there'll be a slight separation. So this is red and this is violet. And then of course you'd have orange, yellow, green, blue, indigo, all in between there, in between red and violet. And so when they exit, they come out and they form that beautiful rainbow that you saw in class today. So when they exit, that's going to be interesting. Let's see what's going to happen here. So we've got, let's go back to that red again. Let's make a blue. Normal. So there's your normal for red, there's your normal for violet. So think about that. Which way are they going to bend when they go from glass back into air? And from our previous knowledge, we're going to say that they're going to bend away from the normal. So here they go. It's going to go down this way. No, that looked like it went straight. Let's get rid of that. Down this way. And this violet light will go down this way. So there we have it. And if you had a screen down here, then that screen would show the separation of white light into its primary colors. So that's pretty neat. And so you can figure all this out with Snell's, still not pretty violet, law. And that, if you recall, that was N incident sine theta incident equal to N refracted sine theta refracted. This is a neat derivation of this from Huygens principle, which we will go over on Thursday, and how this rule came to be, just with some similar triangles in that. So that's it. So let's just do a quick. We got a minute left. Let's just do a quick little. So what would happen if you had a ray of light coming in from air to water? And we'll say that water has an index of refraction of 1.4. I'm just making these up. And air is nice because it's 1.00. It's actually 1.001, but it's close enough to call it 1. So anyway, there's your normal. And what I want you to think about is that we know it's going to refract towards the normal. So there's theta incident. Let's make that 30 degrees. And this is theta refracted. Sneak that in there. And that is 20 degrees. And so with all this, well, I shouldn't have given you that, right? I should just erase that and say, well, can we find what theta refracted is? And so we would say that theta refracted would be then the sine to the -1, solving for this equation up here, is equal to n incident sine theta incident over n refracted. And then we take the inverse sine of that, and that would give us our answer. We just plug in, 1 and 1.4 and 30 or so. So anyway, that's our refraction, a little review of it. We're going to try that as our first little run on letting you sort of watch information, lectures online. Okay? All right. Bye.